Hey guys, I have here a 6000 watt pure sine wave low frequency inverter from SUNGOLDPOWER. This model is split phase, which means it outputs both 120 volts and 240 volts for the North American market. So we're going to take a look at some of the features this device has. We're going to open it up and see how it's built internally, and then we're going to connect it to the Wolf battery from Big Battery and see what this inverter and those batteries can do. So this company reached out to me a couple of months ago now and had asked if I wanted to take a look at and do a review of one of their inverters. And I said, heck yeah, I do a lot of batteries in this channel, but I don't get to do many inverters. So as I mentioned, this is a low frequency inverter, which means there is a gigantic transformer inside, and I can tell it's very heavy. This must weigh, I think it was 85 or 86 pounds, it said in the specifications. Now the design of this inverter looks very similar to some others on the market, as you probably have noticed by now. So on the top here, we have a power switch. The center is the off position. We have power saver on and power saver off modes. We have an LCD display here to show us the status. We have a battery type selector, and we have a series of LEDs here which indicate the status of the inverter. We also have a small dial here to adjust the charging current. So here we can see the different charge parameters, the float and fast charge voltages of those various chemistry settings. And this inverter is somewhat unique in that it has an LFP or lithium iron phosphate mode. In fact, I see there are three modes here. We have classic LFP, we have lithium iron phosphate, and then we have a standard lithium mode. So looking at the side of it here, we have two large lugs for our negative and positive 48 volt input. One thing I noticed that these studs are loose. So I assume when I tighten down these flange nuts, it's going to pull the stud tight. But I want to see on the inside how these studs are connected, because that looks a little bit odd to me that it's loose like that. We have a large fan for cooling. We have a generator start. I believe this is a relay that will flip on or off, so when your battery is depleted, it can flip this on, which will start your standby generator to charge up your batteries. We have a plug for a remote temperature sensor, a plug for a remote control panel. We have a series of DIP switches here, so you can set things like your low battery trip point, AC input range, operating frequency, and your priority mode. So if you want this to operate with utility having priority and operate as a standby UPS, or you can have this running in battery priority, such if you're off-grid. In our cases, we have a larger cooling fan, and this is the end where the transformer is going to be. I can tell by picking it up how heavy this is. We have a circuit breaker for the output line 1 and a circuit breaker for the output line 2. So I know a lot of people don't like this style of connection block, but I actually do like them, and I haven't had any issues. So we've got a ground connector, leg 1 and leg 2 of the AC input. You do not connect a neutral to this. And on the output, we have leg 1, leg 2, and neutral. There is a safety panel that goes over this. Unfortunately, this inverter did suffer a little bit of shipping damage on its way out here. So I know you probably can't see it in the video, but it's dented a little bit here, and this panel got banged up a little bit. So, alright, so there was just a series of Phillips screws around this enclosure to opening it up. Before we take the lid off, I think it goes without saying, you shouldn't be opening these things up. There is potential hazardous and fatal voltages in here. So let's go ahead and carefully remove this lid. Alright, so here's a look at what was inside the lid. And the connectors all have this red sealant stuff on. I actually had to use a flat screwdriver to pry it off a bit, so annoying to take apart, but a good sign of quality in my opinion. Alright, so looking at the internals here, we can see the gigantic transformer. This is a low frequency inverter, which means it's going to have a very large transformer. I'm actually very impressed with how this is put together. These wires are all bundled. They're all individually covered with these long heat shrink tubes. They're zip tied together in neat bundles. I don't see anything. The only place I see a wire rubbing is over here on the neutral. I'd prefer not to see that laying against the transformer like that. But here's a shot of the control board. Again, you can see all the wires are bundled nicely. These two are the power input wires. They are number 12, which at 6,000 watts would be about 25 amps. And I would have preferred to see number 10s everywhere, but they're still within spec for chassis wiring, and the insulation is rated for 105 degrees Celsius. Over here we have the two output wires for leg 1 and leg 2. These are also number 12s. And then we've got a red and black, which go down to a board down here with two capacitors. And then those wires feed into the winding on the transformer here. I also noticed the part number on this control board with the MOSFETs here is any power PCB. When I looked up this part number, It did cross-reference to Sigonier, also selling these PCBs, and I point that out because Sigonier is who we believe to be the OEM manufacturer of many of these inverters that seem to all look the same. One thing I was somewhat interested in is the backside of these terminals that I mentioned seem to be a little bit loose. It looks like they are designed that way. As you can see, there's no nut back there. The end of the screw is confined in this little plastic covering. So it is designed such that when you tighten that flange nut down, it pulls this tight. So we've also got the main positive and main negative where they enter the inverter. We've got very large bus bars here. On the other side here, we can see each of the output legs goes through these circuit breakers. There's a second one over here before going down to the terminal block. Now, interestingly, the neutral wire coming off of the terminal block is the only one that is a number 10 and is not insulated. All the rest appear to be number 12s. That neutral wire comes back over to here and goes into this transformer. This transformer is also fed by AC input. I guess depending on these two relays here appear to be the transfer switch. So I think what it's doing, because it only takes a leg 1 and a leg 2, it must be using this transformer internally as sort of an auto transformer and generating this neutral. And that's something I just learned about recently from watching one of David Paz's videos, which is quite interesting. Additionally, I believe it's also using this transformer for the charger when this charges. If anyone can confirm whether or not that's how this works to generate this neutral, sort of as an auto transformer type setup, please let me know because that's something that's very interesting to me. So looking at the other side of the inverter, again, I'm no expert in the engineering of how this is done, but I can see where we have leg 1 and leg 2 come off the low voltage side, and those are what's feeding into the large transformer. There's also a temperature sensor here affixed to this heatsink. So this will shut down when it reaches a certain thermal level, and it also controls the fan in both the front and the back based on thermal as well. So that fan's actually controlled by thermal and by the actual load, which we'll talk about later. And here's just a close-up shot of these bundles of wires. Again, this seems to be fairly standard for most of these inverters that I've looked at so far, but I'm very impressed with how this one is organized. My Ames inverter was not this neatly bundled. Like I mentioned, all the tiny connectors have that red sealant stuff on just to hold the connectors down from backing out. And there's the one I had to pry off a little bit. So all in all, the level of craftsmanship, you know, I'm somewhat impressed with on this inverter. Alright, so now we're to the fun part of testing what this inverter can handle. So I built this little test board up here for testing this inverter, and hopefully I'll be able to test some more in the future. But I've got a double pole 300 amp breaker that's going down to this 30 amp Drier outlet. Unfortunately, my house still has the old 3-prong Drier. It does not have a separate ground pin. And then I have two single pole 20 amp breakers going up here to these two 20 amp receptacles so we can test loads on each one of the two legs. And I have a jumper installed between the ground bar and the neutral bar. And I did these as two separate bars, that way I can remove this ground wire depending on what inverter I'm testing. And I'm going to connect this breaker panel to my inverter with an old roll of 8.3 Romex. Alright, and here's how I made the connection with that number 8 wire before I close this panel up. I don't often talk about the AC side of wiring on this channel, even though I really enjoy that more than the DC side, just because there's too much room for things to go wrong and people to get hurt. So if you're not sure or not comfortable on AC wiring, please contact a licensed electrician. And that's all I'm going to say on that topic. Alright, so I've got a somewhat large setup here going on. I've got my inverter, my SUNGOLDPOWER inverter. I've got the two big battery blocks. These are 24 volts each. I did charge these up fully a couple of days ago, and I left the parallel cable intact, so they should be perfectly balanced. You can see over here I have leg 1 and leg 2 connected along with the neutral and the ground, the output. I do not have the AC input connected. Unfortunately, I don't really have a good way to test that without having to wire a new 240 volt circuit off my breaker panel, and I really don't want to do that right now. So the first thing I have to do is connect these two batteries in series to get a 48 volt system. Big battery sells these cables. This is a series cable. So you'll see there are two gray connectors, and there's a blue wire coming off that is joining the positive from this connector to the negative of this connector. And then we have this black connector here with a positive and negative. So I'm going to plug one of these connectors into each battery here. It's interesting, when I plugged those in, these displays went off temporarily. I'm not quite sure why that was. So I should have a 48 volt nominal on this plug now. I've got 56.3 volts, and I'm also double checking that the polarity is correct. So on the DC side over here, I also have my Batrium shunt because I want to measure capacity of these batteries under a high discharge load. And then I also have a little fuse brand 225 HRC or high rupture capacity fuse, just in case there are any problems with this inverter. So I'm plugging my black connector, which is my battery, into the battery side of my shunt and fuse. And then I'm plugging the load side of my shunt into this separate connector that's connected to the inverter. So now you'll see I have the black negative connected to the inverter currently, but I have not connected the positive yet. So what I want to do is use this resistor to pre-charge the capacitors in this inverter. Now I don't normally do this step because typically I have a circuit breaker I can flip on, which reduces the need to pre-charge, but in this case I do not. So I don't want to cause any large sparks or anything with this. So I'm just going to connect this resistor here. And you'll see I did kind of get a spark there. This is only a 1 ohm resistor. A higher ohm resistor would have been better. So now I can go ahead and make this connection without a large spark. Now SUNGOLDPOWER also sent out this remote control switch for it, so you can plug this into your inverter and mount this somewhere away from your inverter for turning it on and off. And they also sent me this temperature sensor for the battery. Now we're not going to be testing charge functionality of this inverter just because I don't have an AC input for it. And then before we actually turn that on, I have my Batrium display here. So we can see we're at 56.51 volts and it's zeroed out to 0 amp hours of capacity. So I'll go ahead and flip this switch to on. Alright, so the inverter's turned on. You can see it's idling at 1.86 amps or 104 watts. This is the biggest disadvantage, or pretty much the only disadvantage really, to these inverters, these low frequency inverters, is the idle consumption. So there is no load plugged in and we're sitting at 104 watts currently. And looking at the top of the inverter, we can see this green light is turned on, which means inverter on, battery charger off, and we can see the display cycling through a few different statuses. Alright, so I'm starting to run out of bench space here. So I'm going to go ahead and turn on both of my 120 volt outlets here. We're at 122.6 volts. We're at 122.6 volts, so that's perfect. Turn on my 240 volt outlet, and I'm seeing 245 volts, so that's pretty good as well. So I'm going to plug in my usual space heater here, and it's just this Lasco brand I usually use for capacity tests, and turn on high and see what happens. So no surprise, this inverter has no problem powering that. We're pulling 1.76 kilowatts, 1.81 kilowatts. So what I really want to do to test this inverter is see just how much it can take. So I'm going to plug my clothes dryer into this 30 amp outlet, let that run, and that should pull around 5,000 to 5,500 watts, nearly maxing this inverter out. So next, then I'm going to plug in a couple of space heaters because I want to see really like how much I can overload this inverter. Alright guys, so this is where the test will get interesting. Over here on my Batrium display, you can see we're pulling 5,500 kilowatts from these batteries currently. Now these batteries are rated for a maximum load of 6,000 kilowatts when they're in series like this. I can already feel these cables are getting a little bit warm. 109 amps is a little bit much for 6 gauge wire. And as you can hear down here, the fan on the inverters is turned on. It runs this fan based on temperature or based on load, so it sees a certain percentage of load. Now I was planning to see how much I can overload this inverter, but I'm not really sure how far I want to push it. These cables do feel kind of warm. So yeah, I'm just going to leave that heater turned off, and we're going to let this run and finish that load of laundry, and we're going to see how many amp hours we get out of this battery at a near full load, in addition to how well this inverter performs. I don't know guys, these cables are very, very hot to the touch. I really wish I had my thermal camera. I didn't think to set that up and charge that up ahead of time, but let's see if we can get a reading here at this infrared. Oh, something's shut down. Oh, the heating element in the dryer must have kicked off. So we're at 7.4 amps. We'll have to wait until it kicks back on again. So I see 56 Celsius. Guess it's not that bad. Again, it's hard to get an exact reading here. Oh, there it goes. It's kicking on again. Alright guys, so I removed the top panel of this one big battery here, and the BMS is really just warm. It's this cabling, this black cable here is like scalding hot. 73 degrees Celsius. I'm kind of afraid to continue with this test, to be honest. Yeah, I think we're gonna call this test quits here. Alright, and after all that, this inverter is warm, but it's not that warm. The output terminals are cool, the terminals in the front are cool, the front's cool. There's not a lot of heat being thrown from this inverter. It's just these 6 gauge battery cables are really concerning me, especially in this enclosure. They're getting scalding hot to where it hurts to touch them. Alright guys, so I'm going to finish up this test. I just want to let these batteries run down until they're at empty. So I'm going to plug in 2 space heaters and a series of incandescent light bulbs. So I've got 1 space heater on leg 1 and I've got the space heater and light bulbs on leg 2. Alright, so while the discharge test is running with those space heaters, I want to try one more thing, starting a heavy inductive load. So I have my Cobalt air compressor. This is 8 gallons, 1.8 horsepower. Not many inverters can start this guy, so I'm going to see if this inverter with these batteries is able to do the trick. Here we go. Wow, that sounded perfect. That is awesome. The starting capability of these low frequency inverters is incredible. So I think we're getting near the end here. This has been running for, I don't know, an hour or more maybe. We're at 43.14 volts in the battery, 113 amp hours, and I do not feel the same heat issue as I felt at 110 amps. They definitely do feel warm, but the cables are not warm to the point where it's concerning like before, so. And our voltage is dropping quickly, and you can hear the low voltage alarm of the inverter is now sounding. Alright, and there we go. The inverter shut down. Interestingly, the BMS did not trip, so we're just above the trip point of the BMS. And let's wait and see what our final capacity is. And we finished at 115.64 amp hours. These batteries are rated for 120, so that's not bad at all considering that heavy load we had in the beginning. Alright guys, so there we have it, the SUNGOLDPOWER 6000 watt pure sine wave inverter. And as you saw, the starting and overload capacity due to being a low frequency in that massive transformer is one of the things, or the most important thing really, that makes these inverters so attractive to me. So reading from the manual here, this inverter can be overloaded to 125% its rated capacity, or 7.5 kilowatts for up to 15 minutes. Additionally, it can be overloaded up to 150% for up to 60 seconds. So that is huge. That's 9,000 watts for up to 60 seconds you can put on this inverter. And where that becomes important is like if you're using this for your home or backup, let's say your air conditioner is on or your clothes dryer is on, and not have to worry about shutting something off if you have to flip on a microwave temporarily, your fridge kicks in or something like that. So. And you won't find that kind of overload or starting capacity on a high frequency inverter. So additionally, this has a 120 amp charge controller built in if you choose to use it. I know the inverters and whatnot that I'm running, I typically don't connect the grid input to it. However, this inverter is specifically designed with lithium iron phosphate in mind, so it pairs perfectly with these lithium iron phosphate batteries. Now this video is about this inverter, however I was a little bit disappointed to see these batteries could not push the 130 amps continuous they are rated for. 6 gauge wire, even if it is silicone insulated, just is not enough for 130 amps in my opinion. So I don't know if it was maybe the crimps or something in there that were getting a little bit warm, so the whole wire was getting warm, but either way, I would have definitely preferred to see this battery built with, number 4 or maybe even number 2. Nevertheless, it's still a fantastic battery. I have no problem, 75, 80 amps, something like that through it, but not 110 or not 130. So my biggest complaint, and probably my only complaint about this inverter, is the amount of power it consumes idling. We saw it around 95 to about 105 watts there when we were first turning it on and testing it. I don't know what the deal is where most of that power gets wasted. I know a lot is wasted on the transformer itself, and that's just the nature of having a low frequency inverter. I'm sure there are things they can do to make those transformers more efficient. I've heard people suggesting the toroidal or the round transformers instead of the E-type iron core transformers. I don't know why they're not taking a look at ways they can make them more energy efficient like that. I suppose it also would have been nice if there was a data port we could plug into, or even if I wanted my Baytream to control this, I'm still limited to just turning it on or off based on connecting those 2 pins on the RJ45 connector. But for what this is and the price this sells at, this inverter can pretty much power your whole home, either off-grid or in an emergency situation. Again, depending on the types of appliances you have. So I do want to thank Sunny at SUNGOLDPOWER for sending this inverter out to me for review. It is very much appreciated. I will leave a link in the description of this video to where you can purchase these, to their website, and to the product manual for this if you're interested in more information. Please don't forget to hit that like button before you go. Thank you very much for watching, and I'll catch you on the next one.